Urban air pollution is becoming one of the intriguing concerns in the developing countries like India and many other Asian countries. So, to manage the urban air pollution, modeling is one of the important tool to predict the source contributions and to predict the air pollution levels at various places, and also to analyze those data and come up with some suggestions for the air quality management. So basically, modeling is being carried out across the world, particularly in United States and many other European countries, to manage the air quality of an urban setting. The models can be of different types, namely physical, experimental, empirical, and statistical. In predicting the air quality or in predicting air pollution sources or in predicting the air pollution concentrations at a given location, there are n number of models applied worldwide. But mostly these models are mathematical and numerical techniques. And the model simulates the physical and chemical process of air pollutants as they disperse from a given source. And based on the inputs of meteorological data like wind direction, wind speed, and the lapse rates, atmospheric stability, and the source informations like the stack height, emission velocity of the gas, and also the heat of the gas that is being emitted from the stack. Based on these parameters, the model can simulate the concentrations of the air pollutants in a given or in a receptor location. Basically, these models are designed to characterize the primary pollutants that are emitted directly into the atmosphere. And in some of the models, even the secondary air pollutants that are formed as a result of a reaction between the primary pollutants are also possible. So basically that across the world, there are two types of models that are being widely used. The one is point source dispersion modeling, another one is receptor modeling. Point source dispersion models are typically used in the process to estimate the concentration of pollutant at a given location in the ground level receptors or surrounding an emission source. The point source is nothing but from the stack, you can really predict or model the concentrations at a receptor locations. What sort of pollutants or what concentration of the pollutants will be there at a given receptor point. So this is nothing but we have a known source of stack, and the gaseous emissions from the stack are already determined, and then based on these emission parameters plus the meteorological parameters, a mathematical equation is developed to model the concentration of a pollutant in the downward wind side, or the plume, or the downward plume, or the plume that travels in the wind direction, the wind trajectory. In the trajectory location, in the trajectory, we can model the locations, the pollutants. Whereas in the receptor model are mainly based from the ambient concentrations. Receptors, this is another kind of model where the pollutants or the concentration of pollutants in a given location is being monitored, quantified by various techniques using the measurement equipments like PM10 samplers or gaseous sampling units. And the source In this case, it's like just opposite, where the source is determined from the data which is obtained from the ground level air quality monitoring stations. That is based on the ambient data, we try to predict. So a source model uses the source emissions as inputs and calculates the ambient concentrations, whereas the receptor model uses the ambient concentration as inputs and calculate the source contribution. It's just the reverse. So it's clearly shown in the picture here. The source model, you can see the known source emissions and known dispersion characteristics. So these are the two parameters that are given as input, and it will estimate the concentrations at a desired receptor location. So we can just predict the concentrations at a downwind direction, maybe 1 kilometer, 2 kilometer, or 3 kilometer, whatever it may be. Whereas in the receptor models, the ambient air pollutant concentrations are known through the monitoring stations or the data from the instruments that are used to monitor the air quality. So like PM10 or SOx or nitrogen dioxide, whatever it may be, the pollutant, these are given as input parameters, and the source characteristics or the source profile or the source signature is there already, that is being calculated for certain source profiles. Like for example, if the gasoline is being burnt, what sort of pollutants arise from the gaseous pollutant, the gasoline, are all known, and these have been already derived. And using such known source profiles, we can estimate the source or the source for the pollution in a given location. So data from the receptor location is used to identify the source and also the quantify the source. So let us get into the point source model. Point source model, as I told you earlier, it predicts the concentration at various locations around the source. It is mainly towards the downwind direction. Identifies the source contribution to air pollution area. It assesses source impacts and suggests the control strategies. So these are the main usage of this model. It is mainly used to predict also the future concentrations. If at all there is an industry coming up in an area, what could be the concentration in the downward wind direction or in a given location. So basically, the air quality model is a mathematical relationship between emissions and the air quality that incorporates transport, dispersion, and transformation of compound emitted into the air. So the model is basically a mathematical equation which requires the input parameters like the emission parameters, as I told you earlier, and also sometimes the model parameters like the source profile and the meteorological parameters like wind speed, wind direction, atmospheric stability, dispersion coefficients. These are the parameters given as meteorological inputs, and then the air quality in a given location will be predicted by the model. So this is a broader picture of the air quality models that are being used and the principle behind it. So basically, we can classify as deterministic, statistical, and physical models. And the most widely used is the deterministic model, and which is again the steady state model, and in which the Gaussian plume is the most widely used model across the world. And there have been various models available now based on the Gaussian plume. In the statistical model, and again in the deterministic model, you also have the box model, grid model, spectral, puff, trajectory, and lag, and Eulerian and Lagrangian models. So all these things are based on the mathematical equations. And there are some statistical model which the kind of receptor models like principal component analysis, positive matrix factorization, and multivariate analysis also are used to determine the air quality sources or source apportionment. And also there are physical models that are being which is I think it is rarely used, but most of the models are based on the Gaussian plume model. So a deterministic model calculates the pollution concentration from emission inventory. The emission inventory, as I told you earlier, for example, the emission inventory of the coal industry or a cement industry is known. The gas or the plume that is coming out of the stack is widely known for its nature, and it is being already classified based on the pollutants like sulfur dioxide, nitrogen dioxide. So the emission so the model is mainly based on such emission inventory and the meteorological parameters, which is considered as steady state, or the model considers the most of the meteorological parameters in a steady state, like wind speed is constant throughout the model, and there is no change, and it doesn't it assumes that the model is the wind speed is constant throughout the analysis. So deterministic modeling is a traditional approach for the prediction of air pollutant concentrations in urban areas. So this is as I told you, this is the Gaussian dispersion model. It was developed in 1800s, and it has been updated and modified several times, and several people have modified it, and even it is subjected to modification, and recent versions are available based on the Gaussian plume model. So the Gaussian plume model, as shown in the picture, it has got, as soon as the plume or the flue gas is out of the stack, it tries to move towards the downwind direction, or the windward side. So that direction, is called as x-axis. The movement of plume towards the wind or the downward wind direction is the x-axis, and then the horizontal movement of the plume, it is given here from the stack. As the plume moves, it spreads horizontally, so that axis is called as y, and then the plume also spreads vertically, so that is the z-axis. So all the three axes are perpendicular to each other. X-axis, y-axis, and z-axis are perpendicular to each other, and there is a central line in the plume. So this considers, the model considers the gas transported downstream. Dispersion in vertical direction is governed by the atmospheric stability, and the atmospheric stability is a natural phenomenon, and the atmospheric phenomenon, which I'll come to it later. The vertical movement of the plume is mainly governed by the atmospheric stability, whereas the horizontal movement, that is y-axis, is governed by the molecular and eddy diffusion. So there are certain coefficients arrived for this under the constant conditions. So the x-axis is oriented toward the wind, as mentioned earlier. So the concentrations are assumed as symmetric about x-axis and y-axis. So you find that on the both sides it is symmetric. The distribution of the pollutants are symmetric. So this is another picture, and as I told you earlier, ZY and X are all perpendicular to each other, and as the plume moves towards the wind direction, windward direction, the diffusion or the dispersion happens in all three directions. So these are some of the models which use the Gaussian plume model, and this has been taken from the US EPA website. You can see the models are ADAM, ADMS, like that. So many models are now available based on this Gaussian plume model. And I cannot tell all are based on Gaussian plume, but most of them are, these models are based on the Gaussian plume model. So the computer software parameters include the pollution emission rate from the stack, that is grams per second, the stack height, then the stack inside diameter, that is the exit diameter. So the gas temperature, that is, it is important to analyze the heat transfer. So the temperature of the gas and the velocity of the gas and the ambient air temperature, then the receptor height, topography, etc. are the parameters that are being used. So this evaluates the pollutants at a given location. So for what all source types these models are being used? These models are used for a typical point source like the stack which you saw in the picture. That is a single emission point from a smokestack with continuous emission rate. And also the volume source, user sets, height, virtual. So this is like a virtual point source. Also we can generate the data for it, like the railway line, conveyor belt, and all these things. And it can also be called as a line source, whereas where a particular highway where you find the movement of the trucks or typical kind of cars. So we can also use this Gaussian plume model to predict the concentrations or to predict the pollution dispersion from a line source. And also it is also used to predict the area source and also the open pit emissions from an open pit, from a mine or quarry, and also from the flaring stations, like any kind of flaring stations where the combustion of like incinerator or LPG or the waste to gas flaring, like that. So again, coming to the same parameters, these are the two basic parameters that affect the dispersion. That is, the source emission rate of pollutants is always considered constant, but it is in real world sometimes there may be change. The stack height is constant. The exit velocity of the gas is also likely to be constant. The exit temperature of the gas is also is likely to be constant. The stack diameter and the meteorological conditions, the wind velocity, wind direction, ambient temperature, and atmospheric stability. But the model assumes that Gaussian plume model assumes that it is steady state conditions, like the constant source emission at strength. There is no change in the gram per second of the pollutants while it is being emitted into the atmosphere. The model considers it as a constant. So if there is any change in the strength of the emission, the model cannot predict it. So the wind speed, direction, and diffusion characteristics are considered as constant. The mass transfer due to bulk motion in the x direction far outshadows the contribution due to mass diffusion. So, and also the conservation of mass, that is no chemical transformation take place. That means the pollutants within the plume does not react to each other, and it remains inert, the model considers that it remains as such from the source to the receptor location. And also the model assumes that wind speed is above, or model uh, works out only for the wind speed above 1 meter per second. And also most of the models are limited to the 2 kilometer from the source, and beyond that it is the model cannot predict the correct concentration, so it is limited to. So this is how the equation is developed based on the Gaussian plume model. And equation for the Gaussian plume model, this is the height of the stack is h. It is normally the small h, and as the plume rises to a certain extent and then it travels towards the x direction, so the topmost height, or it is where the plume starts traveling towards the x direction, so that is called as effective stack height. That is the plume that is released from the stack moving towards certain height and then dispersing towards the x direction, downwind direction. So that point is delta h, and small h plus delta h gives you the effective stack height. Sometimes effective stack height is considered as constant. It is like the stack height is known, h is known, and the h into 1.73 is considered as the effective stack height, that is he. That is, as I said, that is delta h plus h. The delta h is the plume rise. The plume rise sometimes is considered as h plus 1.73h. So here in the picture here you can see, as it moves towards x direction, the pollutants get dispersed and the bell-shaped curve enlarges as it goes towards the x direction. So the dispersion happens, dispersion from the source towards the x happens horizontally mostly, and also the vertically. So as the distance increases, so does the dispersion. So that's all we have for today. Thank you.